Quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right.
You can see it, sir.
Let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So I hope you have seen the video regarding the double slit
Yes. Sounds out of
experiment.
excellent.
Hello, yes? Yes, hello? Shall we share the slides now? Just wait for a while. Please note, I repeat.
Sounds out of blackboard radiation.
Please note, today you will be having the quiz. I repeat, please note, you will be having the quiz, live quiz during the session. Okay, you may get a notification soon in the assignment section. I request the participants to mute yourself. Okay, and I muted it. Okay, so I was, if you recall my discussion when I started the interference, right? So I was mentioning that you will be seeing this double slit experiment multiple times. If you recall in the first chapter, while discussing the Young's double slit experiment, where while discussing the interference pattern, we made certain assumptions such as that you are able to produce the interference pattern where the diffraction effects were negligible, considering the fact that the slit width of the slit is very, very small compared to the wavelength of light. That's what we have discussed. A is very, very small there when compared to the wavelength of light. See, who is Pollu? Sarasada, please mute yourself. Please mute yourself. So in the interference Young's double slit experiment, we consider that the width of the slit A is very, very less than wavelength of light, and in that case, we have observed an interference pattern of alternate bright and dark bands. Of you can see the intensity where there was almost equal. So basically, due to the fact that diffraction effects were not considered. But the moment you relax the condition, this condition of A is very, very less than lambda, you notice that the diffraction effects comes into picture and all the interference pattern gets perturbed, and that means you will see the diffraction pattern where you will see that intensity of the bright bands are not same as in case of the interference pattern, and also you will see some of the interference bands will be missing. Now, those were considering the fact that the wave nature of light, the interference experiments were considering the wave nature of light. Now, we are doing the same experiment, but with using the particles. So the particles here are these electrons. The electrons are made to incident on the double slit, and well, there will be a detector over the screen. So the detector will act like a viewing screen, which produces the interference pattern. So a parallel beam of monoenergetic electrons is made to incident on the double slit, and you will see that the interference pattern which is produced on the screen. So you can see over the detector in the blue color. So this acts as a viewing screen. So here the slit separation D is much greater than the slit width, like in case of the Young's double slit experiment, and much less than the distance between the slit and the detector. That is this distance, which is same as YDS experiment. So here the electron detector is movable along the y direction, so that it is able to record the electrons, collecting the pattern, collecting basically the electrons, so that the interference pattern can be produced. It is able to move at different values of theta. So as I was mentioning, the detector here acts like a viewing screen of Young's double slit experiment. So this is the viewing screen here. Now, if you can see here the photograph of double slit interference pattern produced using electrons. Please note this is using electrons. That is, you are using the particle to produce an interference pattern. So from it is clear that what we are studying in the past few classes, that is the wave nature of the particles, right? So like for example, you can the de Broglie hypothesis that all particles exhibits wave nature. You can see this is another experiment which demonstrates that you can have an interference pattern using the particle. So in this case, you have d sin theta is equal minimum occurring at an occurs at condition d sin theta is equal to lambda by 2. So one thing you need to note here is you'll be using the electron wavelength. The moment using the electron wavelength, you need to use the de Broglie equation. Lambda is equal to h by p. For small angle theta, sin theta is equal to theta lambda by 2d or h by 2pd. So you will be, since you're using a particle, so you have to use the concept of matter waves or the equation for particle given by the de Broglie hypothesis. This experiment proves that the dual nature of electrons, that is, electrons are detected as particles at the localized spots. Okay, so they are detected as particles at the localized spot at some instant of time, but the probability they arrive at the spot is by finding the two intensity of interfering waves. That is, the probability of arriving is a wave, and they are detected as a particle at the localized spot. So this experiment is one which proves the dual nature of the electrons. So electrons are particle which exhibits wave nature. We have seen in the photoelectric effect and the Compton effect that you have seen we shine a light over the or the metal surface or even in the carbon targets where the electrons are there. You will see that particle nature is exhibited. Here you are shining a particles and you will see the wave nature is exhibited. So the dual nature of electrons that is which exhibiting the wave nature is confirmed by this experiment. So as I was shown in the video, so you might have seen the video with a couple of cases when they were firing the marble and then they're firing the electron at change it to electron, and you'll see various type of pattern was produced. Here, suppose if you block slit 2 for half of the time, so slit 2 half of the time, keep the slit 1 open, and then what you do is block the slit 1 and keep the slit 2 open half of the time. You will see that the counts observed is in blue color. Okay, so that is, it will be the pattern which is produced is not an interference pattern, just two lines, in the sense that two intensity will be produced, the interference pattern will be lost. Now suppose if both the slits were kept open, then what you get is an interference pattern, which is shown over here in the brown. This is the interference pattern which you can notice here. So the observed interference pattern when both the slits are open suggests that each particle goes through both the slit at once, right? So this is something hard to believe, but we need to accept it based on our experimental result. That is, we are forced to conclude that the electron interacts with both the slits simultaneously, detaching its localized behavior. Okay, so that means we have to make a conclusion that the electrons are interacting with both the slits, detaching its localized behavior. When I say localized behavior, that is, it's detached its particle. Particle means it's a localized picture. You know the location where the particle is.
Sure.
So if you try to find which slit the particle goes through, what you observe here is the interference pattern vanishes. What does it mean? That means if you know the path at which this particle is taking, we lose the fringes. So at the end, only we can say that the electron has passed through both the slits. So it is hard to believe to accept it, but the thing is, what is actually happening here is the wave components. Please note the wave components of the electrons are present at both the slits at the same time. Okay, it is the wave component which is present at both the slits. Yeah, somebody was asking a question. Yes.
Sir, to me, only the first slide is visible, sir.
Huh?
To me, only the first slide is visible. The
What about
introduction
others?
of physics.
What about others?
Sir, only first slide is visible, sir.
Sir,
Only first slide.
sir,
Sir, what you're teaching is visible. Sir, they can
Sir.
leave the meeting and join again.
Yeah.
Yeah, sir.
Those are issues. Those who have issues, what you do is leave the meeting and rejoin it. Others are able to see the slides?
Yes, sir.
Yes, sir.
Okay, fine. Those who have an issue, please leave the meeting and rejoin. There may be issue from your end. Okay. So I hope this is clear to you. This concept is clear to you all. Anyone has a query in this experiment? So this experiment proves that the electron possesses the dual nature, a particle exhibiting wave nature. That is, interference and diffractions are the experiments to confirm the wave nature, right? So this is a particle which exhibiting wave nature. Yes.
Excuse me, sir. Can you go back to when you said how a observer can collapse the wave nature? So
Yes.
right here, the last slide.
See, by looking at the experiment, if you are assuming you are getting an interference pattern, then the particle we have no other option left to conclude that the electrons were present at both the slits, right? When you say the moment the electron is present at both the slits, because we all know that electron is a particle, that means it requires the localized nature. That means it is shedding the nature of localized behavior and behaves as a wave. That means what we can say from here is it is wave component of the slits. Or in simple terms, we can make a conclusion that the probability of arrival is like a wave and interaction with the matter is like a particle. Is it clear? We can make a conclusion based on the experiment that the probability at which this particle arrives is like a wave and the interaction with the matter is a particle. In the matter is, suppose you have a film on which this particle is colliding to form a pattern. Whenever there is an interaction with the matter, it acts like a particle and the probability of arrival is like a wave.
All right, got it, sir, got it. Thank you.
Okay. Please note, when we say that electrons are present simultaneously, its wave components are present at it. So we can say that it's shedding its localized nature and acting like a wave when it is entering the slits and exhibiting the particle nature when interacting with the matter that is on the viewing screen. So we have seen the couple of experiments in this chapter, that is starting from photoelectric effect, Compton effect, which explained the particle nature of wave, and we have here the Davison-Germer experiment, Higgs-deposit experiment, GP-Thompson experiment, which all are done with the electrons, which are the particles exhibiting the wave nature. So now it is an accepted fact that the particle, all forms of matters as posted by de Broglie, perhaps exhibits wave nature. Only thing is we should be able to detect or not. The problem with the particles is the wavelengths are very, very short. So only if you are able to produce an interference pattern, we can say that it is exhibiting it. But we will not be able to observe due to the limitation of the diffraction phenomena to carry out because of shorter wavelengths. Okay, now coming to the uncertainty principle. So this is the last part. So quantum theory predicts that it is fundamentally impossible to make simultaneous measurements. So simultaneous measurements of what? Particles' position and momentum with infinite accuracy. Okay. So this principle is known as Heisenberg uncertainty principle. So quantum theory predicts that it is impossible to make simultaneous measurements of particles' position and momentum with infinite accuracy. So this principle is known as Heisenberg uncertainty principle. For example, for a particle to be represented by a monochromatic wave existing throughout a space, lambda is precisely known, right? If lambda is precisely known by the de Broglie hypothesis, lambda is equal to hp, momentum is known accurately. So once momentum is known accurately, but the position of the particle in this becomes uncertain. If you are able to precisely measure the momentum, then it becomes the position of the particle becomes so that means when delta p is 0, but the delta x turns to infinity. So I'll explain using this image. Just a minute, they remove the error. Okay. Now we can see here in the first case, when delta x is small. So when delta x is small, what will happen is you'll be able to locate the particle more accurately. See, that is, the delta x is very, very small, so we can more precisely determine the position of the particle. But the problem is you will not be able to determine the wavelength. That means the momentum will be large. So if you are precise in the position, then uncertainty in measuring the momentum becomes large. Now, take the second scenario where you are seeing here the delta x is large. So here precisely you'll be able to measure the, let's say, at a great accuracy, you'll be able to measure the wavelength. That means you will be able to measure the momentum. So, but the position in measuring the position becomes difficult. Sorry. Yes, a position becomes difficult because of large delta x. When the delta x is large, you will not be able to measure the position accurately, but you will be able to measure the wavelength, so that momentum can be measured with greater accuracy, but position is lost. Is it clear? Anyone has a query in this? So Heisenberg uncertainty principle states that it is impossible to make simultaneous measurements of particles' position and momentum with infinite accuracy. So here the two components we are talking about, the position as well as the momentum. So in the first case, I repeat, when the delta x is small, I'll just erase it. So when delta x is small, so what is happening when the delta x is small, it's difficult to estimate the wavelength, but you can easily estimate, precisely you can estimate the position, but the momentum is larger. Whereas in the second case, when the x is large, so the uncertainty in measuring the position becomes large, whereas uncertainty in measuring the momentum becomes small. So this is known as the uncertainty principle. Here the two uncertainty we are talking about is the delta x and delta. Given the equation as delta x into delta px is h by 4 pi or h cross by 2 in some textbooks you might have noted. H cross means h by 2 pi. So if the particles whose momentum is given by is delta p and delta x, you can write delta x into delta p x as h by 4 pi. So similarly, we can also write for uncertainty in energy and time, where delta E and delta T are the two factors. Delta E and delta T are the two factors. So uncertainty is delta E and delta T. So uncertainty in measurement delta X is small, then uncertainty in measurement the delta Px will be large. So if the uncertainty in measuring the delta Px is small, then the uncertainty in measuring the delta X will be large. Is it clear? So I'll repeat. So Heisenberg uncertainty principle states it is not fundamentally possible to make the two quantities which are measured simultaneously with infinite accuracy. Here the two quantities I'm talking about is position and momentum. So uncertainty in position is small, then the momentum will be large. So an uncertainty in position is large, then uncertainty in momentum will be less. You can't measure both with a greater accuracy. That's what uncertainty principle talks about. Is it fine? Anyone has a query? So we have two relations pertaining to uncertainty, measuring the uncertainty components. One is position and momentum, another is energy and time. Do anyone has any query in this?
No, sir.
No, sir.
Okay, so it is, you may get a notification of the quiz anytime from now. Okay. Time for live quiz. So you may get any time now the notification for the quiz. Good luck to you all. There are two questions in that. Try to answer both. Okay. You will have 4 minutes for that. Okay. So you need to submit within 4 minutes. So it will be live soon. Please check your assignment section. Okay. Wait for the notification for it. And followed by we'll have two numericals once you finish this problems. Sorry, quiz. All of you are ready?
Yes, sir.
Yes, sir.
Okay. It is scheduled at 8:35. Okay. I already scheduled it. Please note, we are sorry for that day we had a technical problem with the Microsoft Teams. That's why there was a slight delay in scheduling. It was not distributing the assignments. I'll check what about the assignments. I think it is scheduled. Please check. I think it is scheduled. I think you might have received. Anyone can confirm? It's
Yes,
already
sir.
scheduled.
Yes,
Yes,
sir.
sir.
Yes.
Good luck. Good luck to you all.
ఏంది అర్థం కాలే చెప్పరా
I hope all of you have submitted. Hello?
Yes, sir.
All of you have
Yes, sir.
submitted?
Yes.
Yes.
sir.
Yes, sir.
Okay.
Yes,
I
sir.
hope you have done well in both the quizzes, right?
Yes.
Okay. So I will save the answers later. Now what we will do is I will give 15 minutes break. During that you need to solve two problems. Okay. So after 15 minutes we will discuss both the numericals. Try to solve both the numericals, problem number 25 and 26. Then we will discuss. Hello, welcome back. So I hope you have solved both the problems. Can you hear me? Hello?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, we'll start with the first numerical. So in this problem, the lifetime of an excited atom is 10 to the power of -8 seconds. Using the uncertainty principle, you need to compute the line width delta F produced by this finite lifetime. How much did you get? Hello? Anyone has computed?
Sir, 7.
Yes.
8 into 10.
8 to 10 raised to 6.
7.9.
7.9. Okay, fine. So
Approximately 8, sir. 8 times 10 to the power 6 hertz.
Yes, sir.
yes. You get 8 10 raised to 6 hertz or 8 megahertz. You are right. What about the next problem? Anyone has attempted? I know that this little calculations are involved in it. I hope anyone has attempted it. I hope this problem is clear to you all. You need to use the uncertainty in energy and time relation. Then you can write H is a constant. So what is the varying factor is the line width. So delta F into delta T is equal to H by 4P. Okay. So you have the delta F as 8 megahertz. Sorry, there is a I think due to the mathematical editor problem that the symbols are displaying it as P. It is not P. It is H by 4 pi. Okay, that is H by 4 pi. I think since I am sharing from OneDrive, there is some problem with the equation. Okay. Coming to the next case, you have been asked, use the uncertainty principle to show that if an electron was confined inside the atomic nucleus, that the diameter is 2 into 10 to the power of -15 meters. That is 2 Fermi, I can say. It would have been moving relativistically. When I say relativistically, means at the speed of light. While the proton confined in the same nucleus will be moving non-relativistic. That is very, very less than the speed of light. So you need to show this. For this, what we can do is we can consider the uncertainty has the nucleus, the maximum the uncertainty is 2 into 10 to the power of -15. That itself will take it as delta x here. That is 2 Fermi. And we can have delta px is equal to h by 4 pi. That is not d. That is delta x. So you get the uncertainty momentum as 2.6 10 raised to -20 kg per, meters per second. So you have the mass of the electron is given here. Suppose for an electron, if you use this equation, P is equal to sorry, there was a disturbance. So if you use if you use the non-relativistic equation and try to estimate the V, you will notice that the speed will be 2.85 10 raised to 8, right? This is wrong. So V cannot be, that is, this value cannot be greater than C. So what will be the correct equation? Can anyone tell me to use? Yes? What should we do now? Hello? Anyone? Am I audible to you? Please Let me know.
Yes, sir, you're audible, sir.
Yeah. So just let me know what shall we do now from here. So if you use this non-relativistic equation, you will get greater than the speed of light. So V can't be greater than c. Yes, what is the solution? What equation we need to use? Okay. The better solution will be using the relativistic equation given by E is equal to E square is equal to m square c square plus pc square. So here we have taken E, so that is take square root of half. So you have to use the relativistic equation, which is given as E is equal to 48 ME. We also know that E is a relativistic factor gamma mc square. So if you calculate mc square in MeV, it is 0.11 MeV. So which gives the value of the relativistic factor as 94. Now, so the relativistic factor can be estimated by you have a relation gamma relativistic factor is equal to 1 by square root of v square minus c 1 v square by c square. So in this equation you will get the value as 0.998 times c. So if the electron is confined within the nucleus, right? So that's what the first part was. Using the uncertainty principle, show that if the electron was confined inside the atomic nucleus, which is of 2 Fermi, it would be moving relativistically. So you will see that if it is confined, the speed at which the electron will be moving is 0.9998 c, which is relativistic. Now, for the proton, if you take V is equal to P by M or P is equal to MV, you will see that which is 1/10 the speed of light. See 1.8 10 raised to minus 7, sorry, 10 into x, okay, 1.8 into 10 to the power of 7 meters per second. So meter second. So in that case, you will see that the electron will be moving at a non-relativistic speed. Okay, this is the P is equal to MV is a non-relativistic equation. If it is a relativistic, you will get a factor called gamma. That relativistic factor you need to use if it is moving with the speed of light. So here you will see that the proton, which is confined in the nucleus, will be moving at a non-relativistic speed. So that is 1.8 10 raised to 7 meters per second. I hope you followed this problem. Hello.
Yes, sir.
Okay, so I'll give you time to make so that you can make a note of it. If anyone has a query, you can just ask me. Meanwhile, anyone has a query in this? If you noted down the value, just check the next. So you will get 0.998 C and 1.8 10 raised to 7 meters per second. So those who are completed, So what you can do is after this today's session, so you can solve the problem number 22, 23, 24, and 27, which is related to the topics which have been discussed in today's session. You can do this numerical. I hope all of you are doing the numericals which has been given as a homework to you all.
Yes, sir.
Yes, sir.
Okay, please note, now onwards, for each class you will be having live quiz of composing of 2 marks. Okay. All of you are done with this numerical?
Yes, sir.
Yes, sir.
Okay, so what I will be doing now is I'll be returning you the answer scripts of that summary which you have conducted today. I'll just approving it. Just wait for a while. Now the assignments are being returned. Okay, just wait for a while. Please check your marks. Okay, I hope all of you have checked your marks.
Yes, sir.
Yes, sir.
Most of you have done well. So good that most of you have done well in the live quiz which has been conducted today. So do you have any query in today's class? Please feel free to ask.
So the quizzes are considered best 8 out of 10 now?
Which one?
The live quizzes, best 8 are taken from out of 10 quizzes now?
No, 10 quizzes each carries for 2 marks, right?
Yes.
Yes, we will be notified.
The best 8 will be taken.
Why best 8?
Yes, sir. B sir said that 80% of the quizzes will only be considered. So
okay, that's it. If anything is there, it will be notified to you. Okay.
Okay.
Okay. So now your job will be to read and attempt to write all the quizzes and try to do well in each one of them. Okay? Is it fine?
Yes, sir.
Yes, sir.
Okay. So with this chapter, we have come to the end of the quantum physics. So this will end today's session with a quote. I think I can safely say that nobody understands quantum mechanics. So by Richard Feynman, so well-known physicist to you all. Thank you very much for joining today's session. So before leaving, please stay back. So I'll be discussing with you. So with this, we have completed 3 chapters of engineering physics. That is interference, diffraction and polarization, and then quantum physics. Okay.